Okay, so we are doing recording now. So as we said earlier, this is our main objective today. We are going to cover the ensemble method. Now we can see that in this slides here, they said the techniques to improve classification accuracy. A good example I'll give is that, for example, if we're doing decision tree, let's say we choose let's say C 5.0 using the entropy or Gini index for cat, etc. And we are building only one tree. Then you use random forest using the same, let's say Gini index cat. By this time, you are building 100 trees. No matter what it is, random forest will come out with a good result than only, unless for some reason the one tree that we build, decision tree, give us the best result. So at least the result of decision tree will be the same as ensemble method, random forest. But if there's any difference, random forest will be far better than, because here I build, let's say 10 trees and I let them do all the work, test them. Majority said is yes, and I choose yes. So if I build only one decision tree, if by chance it say no or yes, so that's the whole point. But the reason I'm making this point is that, they say the techniques to improve classification accuracy is using, again, assembly method. So the only thing I will say that in this lectures, we will cover, I won't say some tricks, but I will say that we are going to learn some tricks for increasing what? The classification accuracy. We can increase it. So we're going to focus on assembly method again. And as we said earlier, an assembly method or assembly for classification is just a composite model. It's where we have at least one, two or more models. So it will be a combination of classifiers. And also these individual classifiers, as we said earlier, they are going to, in bargain, they are going to vote. And majority say yes, then we are going to select yes. So I would say that the class label prediction is returned by the assembly based on what? Based on the collection of votes. So again, the assembly method normally would tend to be more accurate than their component classifiers. So random forest will be more accurate than decision tree. And as we said, we have two major methods, which is bagging and boosting. And also maybe I'll say the third one will be random forest. But as we said earlier, we can use random forest means we use only decision tree. So I can use the bagging method on decision trees, and that is again random forest. Or I can use boosting on a decision tree. Then we can also still call it random forest if it's possible. So the only thing I'll say here is that traditionally learning models assume that what? The data classes are well distributed. They are well distributed. So again, in many real world data domains, that is not true. I think we discussed about the class imbalance. Let's say we are looking for this is a positive or negative. Our training data set, we have 100 records. 70 say positive, 30 say negative. This can have effect. So again, we discuss about, and one of the ways that we can, I think we said that some time ago, that one of the ways we can solve class imbalance is maybe to resample the data, take a new sample, or remove majority, but if our data is very small, maybe we may have overfitting problem, or the data is too much. Either one, either overfitting, underfitting problem. So these are some of the issues that take us to the point, or even in this section, the textbook mention techniques to improve classification is again using assembly method. So now let's start with the first one, which we call the bargain. So some few things. So actually, this diagram also works. Now, let's say, for example, we have a data now, a large data. Then we do a sample with replacement. We collect 10, or let's say here, C1 to CT. So we're able to get T, let's say 10. We're able to get 10 again samples. We created 10 models. Then we have a test data to test each of the 10 models. Then each one will have its own decision, whether yes, no, yes, no, yes, no. So first, we say we combine the votes here. We also apply, of course, we go when we create a model, we apply the new data each one, and then the one with the best result, majority vote will be the best result. So the majority vote. So here again, the steps are given here. Use a combination of models to increase accuracy. So for example, combine a series of k-learn models. Let's say k is 10, which is we have 10 models, with the aim of creating an improved model M star. So that's the main goal. So the first, we will go through, actually here they explain all the three. So the two. So bagging means we average the prediction over a collection of classifiers. As we said earlier, boosting go with weighted vote with a collection of classifiers. So boosting is very important, the previous result of the model. So let's say C1 create model M1. The result of it can influence C2 to do better. No, M2 to do better than M1 using C1, C2. So that's where we come with the idea of weighted vote with a collection of classifiers. Then we have assembly. What the term is combining a set of heterogeneous classifiers. So this gives us the whole general idea, or I'll say the whole general topic we're going to cover here. Again, bagging, boosting, and random forest are the major assembly methods that. So as we said earlier from the slide, an ensemble combines a series of k-learn models or base classifiers. Let's say M1 to MK, with the aim of what? Creating an improved composite classification model, which we call the M star here. That's the main goal again. Yeah, let's wait for a few seconds. If any question, we move on to the next slide. Good. So, yeah.
Professor.
Yeah, go ahead, please.
Can you hear me?
Yes.
Professor,
yeah.
Where I can get these slides? I mean, the Unit 9 Part 2, this slide is not in the folder.
Oh, okay. So what I'll do is that when I finish the class, I will post it in the classroom then.
Sure.
Yeah. Okay. So wait for a few seconds. So that's what we said, the bootstrap concept aggregation. And that's a sample with replacement, which means one data can go into two different samples. Yeah. So that's the algorithm that sets. Now, before we go through here, see, this is let's go through the algorithm here is more better. I like the way they write. I keep saying so. Here we have examples. That's why the slides are very long. They give us some example, but I want to go straight to the algorithm here. In mathematics form, mathematics. So this is the bagging algorithm. What we do is that we say let K be the number of bootstrap samples. So if I take 10 samples, we are using the in statistics. Bootstrap means you're taking sample with replacement. So one data, as we said earlier, it can be in 2 samples, 3 samples. So that's the first step. We get the number of samples we need, let's say K. The number of samples will tell us the number of models we are going to build. So here we use a for loop now, from 1 to K. We go using the samples. We create the bootstrap sample of a size. We train the classifiers. So if it's K, we are going to create or train K classifiers. Using what? The bootstrap samples. If it's K, then we have K samples to create each one. So that's the end of it. We create the training model finish. Now our goal is we are kind of the algorithm didn't go detail on this here, but this is computer science algorithm. So what we get here, see, this is our best model. We use the term, let's say the mass or argue mass of the Y. So here, what we are trying to say here is that we have the Y is our target variable. Let's assume, not assume, that's how it is. So S is the independent variable, the features, the Y. So here, as we said earlier, we have our model. So we use the test data to test it. And the ones that get the majority, so that's the mass, the majority vote will be the model that we're going to use, the result we're going to use. So if majority is yes, then it's yes. If it's no, then again, no. So let's wait for a few seconds. Now we can a little bit go in the form of the English, kind of the more in a formal English form for us to understand. Yeah. So actually, this textbook gave us idea. They gave us some analogy here that diagnosis based on multiple doctors. So again, I don't have the test. We are not using this textbook, but what this means is that, for example, we have a disease. Now, let's say a person have disease B, and he visit 20 doctors. So that's why we say multiple doctors. Out of these 20 doctors, let's say 15 said they have the disease, and 5 said they didn't have the disease. Majority vote. So that means you have the disease. So that's all how we will explain on that section. Then when we understand this, I think the algorithm become more straightforward for us. So let's say, for example, here we say, okay, you're giving a set, let's say a data set, D, that let's say D will be like a database. Then we have D tuples. Again, this textbook, the author is very good. He started with database. So he likes to use the database terminology. We know tuples can be features or records, I can say. So again, given a set D of D tuples, the bagging works as following. So we even saw the algorithm, so the iteration. Then also, as we said, I don't want to mention one. So we do with replacement. We have the data set, a training set DI. So if it's D, we break it to 10, D1, D2 up to D10 with sample with replacement with Stripe. And as we said earlier, we're going to use it. So that would be a training data set. Actually, that's a training set DI. So this D is a training data set. So we are going to use it again to build our model. Yeah. We'll wait for a few seconds if it's okay. As we said earlier again, the sample is with replacement from original set of the tuples, let's say the D, the data set. And as we said earlier, so bagging normally means bootstrap aggregation. That's why we have here the bagging bootstrap aggregation because of the way we collect, again, our data. So if no question, then again, I'm repeating myself here. As we said, a classified model MI is learned for each training set DI. So again, if it's 10 training set, we build 10 models. Then to classify an unknown tuple, or let's say unknown record, X, now each classifier, all the 10 classifiers, each one will return its class prediction. So what I'm trying to say here, I said it earlier that we create the model finish, then we use the test data to test it. But I didn't mean that we are going to divide the test data into 10. You use the same test data to test all of them. Then we finish. I think that's the last thing here. The most vote will be the one we will pick. So wait for a few seconds if it's okay. So the last thing I'll say here is that, again, the bag classifier, which is the M star, again, counts the vote and assign the class with the most majority vote to the X. So in short, I can say that bagging can be applied to also the prediction of continuous values by taking what the average value of each prediction for a given test tuple. That's the thing we didn't mention, which is mentioned here. Now, if we are using yes, no, we take majority. The majority vote, yes, no. Majority is yes, no. Now, if it's like a card, we are using value, then all of them, we average all their result. But most of the time, again, now, if we are doing here, I didn't assume decision tree most likely by vote. Random forest will tell us only by vote. But here we are general, as we said earlier, bagging can be used in, let's say we can use it in regression, and regression predicting a price. So, of course, it can't take majority vote. I mean, it can take, but the way algorithm is designed, we take the average of yeah. So that's the end of the algorithm. That's all. So that's what we said today. We have time. Okay, so this is some few things we can say. The accuracy issue. They say often significantly better than, so that's what we said earlier also. We even compare random forest with decision tree. Always random forest is better than decision tree. Now for noise data, not considerable worse, but it's more robust. More robust. Also, it can be improved accuracy in prediction. It has proved that the concept improve accuracy in prediction. So that's all we can say in bagging. Let's wait for a few seconds if any question. So one more time, the other slide they didn't mention it, but we can use bagging also for prediction, or in general for prediction of continuous value as we see it here, which this section they mention. Now, if no question, let's go to the other slides. Then we look at some examples if there is. We already went through the algorithm. Let's look. The example is here. So they say, for example, suppose there are 25 base classifiers. Now you have 25. So this is assembly method. It doesn't matter whether bargain, boosting, or random. In general, we have a 25 base classifiers. Each classifier has a error rate of 0.35. This is basically we just assuming this. Now we say majority vote of classification used for the classification. Now, if all classifiers are identical, so here we are assuming all of them, the same error they make, all the 25. And also if all classifiers are independent, which means the errors are not really uncorrelated. There's no association between each errors. Then the error rate for ensemble, that's we combine the 25, will be probability of having more than half of the base classifier being wrong. And that's the formula here. So go from 13 to 25, error, and that will give us 0.06. Now, the reason why they give us this example, we can see that each gave 0.35 error, but the E assemble for all the 25 from 13 to 25, you can see that the error is way lesser. I mean, 0.06 compared to 0.35 if it was only one. wait for a few seconds if it's okay. So that's one good example they gave us. Necessary condition for assembly method. So the other slide didn't mention, but this is something we should know. I think the classifiers, they don't have to be related to each other. And of course they are not, but this slide make it clear for us, because if you are taking a random sample, if you are doing a research and I'm going to use two samples and I take the two samples randomly, hardly before they will relate to each other, unless I place some criteria condition and take the sample. That condition can create the relationship between the two samples. By the term random, there's no relationship. But here they just want to make it clear for us. So all base classifiers are independent. And also all base classifiers perform better than random guessing. This is for binary classification concept. Wait for a few seconds so we can see the base classifier error and also the sample. This is okay. So if no question, let's keep going. So what are the rationale for assembly learning? They said, okay, so this also very good. Assembly method works best if you have unstable base classifiers. So classifiers that are sensitive to minor perturbations in training set due to again high model complexity. So example will be artificial neural networks or even unpruned decision trees. So I think this section will make us think, before we do any bagging or boosting, we should consider the type of model we are going, what type of algorithm say, and then support vector regression, which one we should use. Because the main thing here should be unstable base classifiers. And I think that's it. The rest, this is about variance and bias and reducing it. And this is, we already discussed this. So here now they teach us how we create it. You have a training data. The first step, you collect all the number of samples you need. Second step, use a test. You build a model from the sample. Again, as we said, use the test set to test all of them. Then combine the classifier responses by using what? Majority vote or weighted majority vote. Yeah, so weighted is where we are going next, which is the boosting. The boosting. So this is in general, if we want to construct a sample classifiers, first manipulating the training set. Either use bagging boosting, also by manipulating the input features. This will be random forest concept. Or manipulating class level. That's error correcting output coding. Or the algorithm, manipulating the learning algorithm. Example, we know artificial neural net, we talk about it. There are some weights that the nodes connect to each node, weight in the, so here they are telling us inject randomness in the initial weight of the ANN. So again, depends on the algorithm. Other than that, I think that's it for bagging. And we already discussed this. And there's an example here also they use. You can take a look at it. And that will take us to boosting. It's almost 1 hour now, so let's take a short break. Then when we finish the boosting and the random forest, then we take the quiz. Now, if we don't have no time for model evaluation, we don't need to do it because we will see everything. We are almost repeating all the evaluation we learned from other models. So let's wait for a few seconds, if any break before I pause there. Okay. Actually, let me stop it. We finish with back again.